So first of all, thank you very much for giving me the opportunity to share my research here. And as you have already heard the whole afternoon, chemical spaces, ultra-large chemical spaces are very attractive at the moment in pharma industry. And with the large size of these spaces, now the question comes how to compare them. And about this topic I would like to present. At the beginning, I would like to thank Christian and Mark from Feasibility, which participated in the study which I will present now. And we have published the whole study in ACS Medicinal Chemistry Letters, so that you can get more details if you want to afterwards. So as an introduction, now, Matthias, you see the slide you missed before in a different version, which I kindly got from Christian. So the whole number of spaces is erasing. You find different fragment spaces from pharma companies. You have also the fragment spaces from the suppliers, besides of some enumerated spaces and the knowledge space of Feasibility. And now the number of spaces is increasing and raising, but also they are growing exponentially. And this leads immediately to two main questions. First of all, is it reasonable to expand existing ultra-large chemical spaces further and further? And the second one, if you have access to one ultra-large chemical space, is it useful and or necessary to search in additional spaces? And this leads to the question which I put as a title, or chose as a title of my talk, how to compare ultra-large chemical spaces. Of course, the comparison of chemical spaces is commonplace. It has been done since decades. You can do exact matches. You can compare the ranges of physical-chemical properties. That's all clear. But these methods are only suitable for enumerated structures. And now with the large fragment spaces, we don't have enumerated structures any longer. So the obvious solution, of course, is to compare now random enumerated subsets. But this gives at best a rough estimate of any overlap due to the vast size of spaces. And so we thought perhaps it's better not to compare random subsets, but to compare search results in the spaces for a panel of query molecules. And the idea behind this is that any overlap of vast chemical spaces, if it is present, should be detected when comparing molecules similar to particular queries. And with this, I would like to describe what we did. First of all, we chose 3 different chemistry spaces for the study. That's the BI space from Boehringer Ingelheim, which is based on thousands of combinatorial libraries with different scaffolds and variable R groups. Then we chose the real space from enamine, which is built from reliable reactions and validated in-stock building blocks. And last but not least, the knowledge space from Feasibility, which is generated from literature reactions and commercially available fragment-sized reagents. All the spaces have grown since we performed the study, so the numbers shown here are a little bit less than those published in the meantime, but when we performed the studies, the knowledge space contained about 10 to the power of 12 compounds, the real space 10 to the power of 10. And for the BI claim space, we don't know exactly how large it is, but it is approximately, or at least this part of this, which was used for the study, that the size is comparable to that of the knowledge space. And then for some experiments in the study, we also used the zinc collection with 10 million compounds. This is an enumerated space, and it's a vast collection of commercially available compounds from various sources. So one last word to the color coding, which you see here. On the next slides, I will show you different figures, and I will always show the BI claim results in blue, real space results in red, knowledge space results in green, and if the single collection is included, then those figures or components are shown in green. So what did we do? We selected randomly 100 query molecules from known drugs with more or less drug-like properties for small molecules. The properties were number of Lipinski violations below 2, molecular weight below 600 Dalton, CFP below 6, total polar surface area below 150 square angstrom, number of rotatable bonds below 12, and at least one H bond donor or acceptor should be present. And having chosen those query molecules, we determined 10,000 nearest neighbors for each of the query molecules in each of the 3 fragment spaces using feature trees FS. And as a result of this, we got 10,000 hits per query, so 1 million compound from each space. So this is the theoretical number. In reality, we got slightly reduced numbers, so only nearly 1 million compounds per space. This is because some of the hits showed up for more than one query. And now we determined the overlap of those hit sets from the 3 spaces using exact match searches, and this is the result. If you look at this, the overlap of the spaces is surprisingly low. I wouldn't have expected a high overlap, but this is really low. You have only below 0.2% of the hits which were coming from at least 2 spaces. And there are altogether only 3 compounds which were retrieved from all 3 spaces. And these were all hits from 1 query. And just to give you some more statistics, for 49 out of the 100 queries, we did not see any overlap among their hits. And for the remaining 51, we saw on average 32 of 10,000 hits from 2 different spaces. So we asked ourselves whether this is probably because simply the method does not work. And so we put together a new experiment. Now we applied the same method as before to fragment spaces with known overlap. And to construct fragment spaces with known overlap, we chose the knowledge space, built from 118 reactions encoding 10 to the power of 12 compounds. And this was split into 2 parts. The first split with 58 reagents, and the second with 8, built from 60 reactions from those. And so we got 2 parts of comparable size, each encoding about 550 billion compounds. And now we repeated the whole comparison. We searched 10,000 hits for the 100 queries from the knowledge space and the 2 splits. And here's the result. So this is an artifact of the Venn diagram, which cannot be shown, but if you look at the compounds which are part of the split 1 and the knowledge space, this is approximately half of the million hits. And the same is true for those compounds which are part of split 2 and the knowledge space. And so, as expected, the hits from split 1 as well as those from split 2 show an overlap of about 50% of the hits of the knowledge space. So, having seen this, we wanted to see some more results, or wanted to analyze the hits further. Now we focused on the coverage of the relevant pharmacophore space. And how did we define this space from our virtual screening experience? We are mostly looking for feature tree hits with a similarity above 0.9. And we simply defined this as a limit, which does not mean that compounds with a lower feature tree similarity aren't valuable. But this was just for definition to look at a certain part of the space. So we determined, first of all, the number of hits with feature tree similarity above 0.9 for each of the queries in the hit sets of the tree spaces. And then here are, first of all, the results for the BI claim space. We sorted the queries according to an increasing number of hits with the feature tree similarity of 0.9. And what you can see is that for the BI claim space, for most of the queries, all 10,000 hits have a feature tree similarity above 0.9. And there are only a few with also hits below 0.9. But for almost all, we find a reasonable number of hits with a feature tree similarity of 0.9. Now, we did the same thing for the other spaces, and I included it in the graph, keeping the order of the queries. And this looks like this. So you can re-recognize the blue curve here. Then we introduced the real space results. Here you see also queries which have 10,000 hits above 0.9, and then the knowledge space results where you have here also hit sets with 10,000 hits above 0.9. But generally, you always find reasonable, or in most cases find a reasonable number of hits with a similarity above 0.9. So altogether, you see that the number of hits with feature tree similarity above 0.9 for each of the random queries varies significantly from query to query and from space to space. But usually you can find high similar hits from all three spaces. And even if the similarity is below 0.9, it might be a good hit. This is out of question, but I wanted to show the differences. You can get hits with high similarity, and the hits or the similarity varies from query to query. This can be also shown using a slightly different measure. In this time, we determined the average feature tree similarity of the hits to each of the queries. And the results are shown here. So for the 100 hits, for the 100 queries, we got 100 average feature tree similarities, the hits, and the distribution is shown here. And clearly, the BI claim similarity, or the similarities of the hits in the BI claim space are higher than those of the others. And the knowledge space and the real space hits show similarity. But altogether, we find a high similarity in all of the spaces. This result can also be shown in a box plot. So these are the same results feature trees, average feature tree similarity, the queries in the BI claim space is 0.94, and those for the knowledge space and the real space 0.89. And now we try to broaden the whole statement. And for this purpose, first of all, we added the similarity searches in the sync collection. So we took the same 100 queries, searched in the sync collection, and determined the feature tree similarities. Here, the feature tree, average feature tree similarity is only slightly reduced. And then we said, well, might be that this is only an artifact due to just to the queries we searched. So we chose new query molecules, new query panels. And this time we chose 100 queries from the different spaces. So we repeated the study 3 times with one time with 100 queries from the BI claim space, with 100 queries from the knowledge space and from the real space. And the result looked like this. This is what you already saw before. And now here are the results for the BI claim space queries, for the knowledge space queries, and for the real space queries. Altogether, you see the same trend, the highest similarity for the BI claim space hits, and the lowest for the sync database hits. So it's the results are not depending on the queries you choose, but there's a slight trend to have slightly higher average feature tree similarities of the hit sets if you choose queries coming from the search space. So just to explain this, here are the results for the queries from the real space. And if you look now at the average similarity of the hits from the real space, they are here higher than for the other queries. But this is only a slight trend. Here you see it also for the BI claim space. Here the similarities are slightly higher than for the other query sets. Well, having seen this, we were interested in the density of the spaces, and to model or to present the density, we looked at the structural similarity of the compounds within a hit set. And to determine the structural similarity of compounds within a hit set, we used the MDL keys just as a commonly accepted measure for structural similarities. And we did the following. We, first of all, for the BI claim space, looked for each member of a hit set and determined its nearest neighbor within this hit set using the MDL keys. So 100 queries, 100 hit sets, 10,000 hits, and the 10,000 hits each had a nearest neighbor. And those 10,000 hits or similarities to the hits were averaged. So we had an average Tanimoto similarity to the nearest neighbors for each hit set. And then we sorted the queries according to ascending average Tanimoto similarity and plotted them. And here, first of all, you see the results for the BI claim space. Here at the beginning, number 1 is the first query with the lowest average similarity to the nearest neighbors in the hit set. What you can already see is that the similarity within this hit set is, or within the hit sets, is really large. And now we wanted to see how is this in the other spaces. And for this purpose, we now repeated the whole thing and sorted now the hit the queries for each space separately. So this means that now the first query might be a different one for the three spaces, for the four spaces. But what you can see is that you have high density in the BI claim space, slightly less density in the real space, little bit less in the knowledge space, and of course the sync collection is less densely occupied. So the most dense occupation of the BI claim space is probably due to the special scaffold-based setup of the fragment space. Here we have it's based on a unique number of on unique scaffolds, and the number of those unique scaffolds is significantly higher than the number of reactions in the other spaces, and so this might lead to this extremely high density. Yeah. Okay, last but not least, we looked at the chemical feasibility, and here we chose two different methods, or two different scores. One is the RSYNT score of Mo, which has a score between 0 and 1. 0 means easy, difficult to make, and where you are aiming for high scores for easy to make compounds. The second method is the complexity-based method of Peter Ertl and Ansgar Schuffenhauer. And in this case, the scoring is an opposite to the other one. Here, 0 means easy to make and 10 means difficult to make, so you need low scores in order to have easy to make compounds. So this has to be kept in mind, but if you look at the figures, you see that the compounds from the zinc database have the highest similarity within the highest chemical feasibility within the four setups. And if you take into account that these compounds are have been synthesized, you can accept them as a reference and say, well, they are at least reasonably accessible. And if you then compare the chemical feasibility of the other fragment spaces or the hits from the other fragment spaces, they are only slightly worse in both cases. And the range altogether is narrow, we have only small differences. Nevertheless, we have a trend that the compounds from the real space have a slightly higher chemical feasibility than those of the BI claim space, than those of the knowledge space. And this is clearly due to the setup. The real space has been optimized for chemical feasibility. In the BI claim space, you find different levels of chemical feasibility up to ideas. And the knowledge space has not been optimized according to chemical feasibility and is based only on generalized literature reactions. And this leads me to my summary. The comparison of ultra-large chemical spaces can be achieved by analyzing the results of similarity searches with a panel of query molecules. This way, the comparison is focused on parts of the spaces where there might overlap. And in this study, we had 3 spaces which had an extremely low overlap. The coverage of the drug-like portion of the chemical universe, illustrated by the similarity distribution in the most similar hits, is generally quite high for the 3 spaces. And the predicted chemical feasibility is reasonably high compared to values obtained for existing compounds. And altogether, the slight differences we saw between the spaces can be explained by their design and their setup. And this leads me to my final conclusion. First of all, the ultra-large chemical spaces contain a lot of valuable starting points for drug discovery. Searches in these spaces have a very high impact in practice. And this answers my main questions. For the detection of alternative hits and potential leads, it's worthwhile not only to extend the existing spaces, but also to explore different spaces. And with this, I thank you for your attention, and I'm happy to take your questions.